Okay, day 2 of section 5.9, we're still looking at the volume of a solid by plane slicing. We'll do one of the volumes of revolution just as a review and to kind of introduce a new concept with it to make sure we understand. But our emphasis today is going to be on volumes of cross sections. Those are completely different in terms of the way that you approach them and the thought that you put into them. So we want to be sure that we look at those and understand those. Again, we're spending time on this through next week, so make sure that if you've got questions, you let me know. All right, I'm going to open this up and slide all the way down because this one is all combined, and we did part of this already. Okay, so we're going to start right here. We want to talk about, and we talked in class about going around some axis other than the X or Y axis. So we want to look again at going around a different axis and kind of make sure we understand. A region enclosed by y equals x and y equals x cubed, that's going to be a function that comes in, looks like this. Your y equals x is coming like that, and your y equals x cubed is this piece right here. It's going to be rotated around. Again, this is in quadrant 1, I should say that, a quadrant 1 region. Is rotated around the line x equals 1. Okay, well, x equals 1 is going to be right here, and so there is my axis. Now, when I swing that around that particular axis, then that means that what I have is on the outside what looks like a cone. Okay, you've got an ice cream cone on the outside, but on the inside, instead of going straight down, it has this little funnel shape cut out of the middle of it. Okay? So I'm looking at something that on the outside looks like a cone, but on the inside it has a funnel shape to it. I'm supposed to write an integral. I don't have to integrate it, I just have to write the integral. Okay, because this one is going around this vertical axis right here, vertical axis, then I have to do everything in terms of y. I cannot leave it in terms of x, even though that was given to me. Okay? So where I have y equals x, well, that's pretty easy. X equals y. Okay? And where I have y equals x cubed, that's going to give me x equals the cubed root of y. Okay? The other thing that we've got to know on this is for sure where we're integrating. This one, again, is going to be going from down here to up here because it's in terms of y. So I need to set my set my y values on this so that I can find my y's. I was just looking because that is not the most fun thing in the world to do. Cubed root of y. Okay, if I cube both sides, if I cube both sides, that's going to make this be really ugly in terms of solving. So let's go back and let's look at our x's and see if we can figure it out that way. If I set x equal to we'll go ahead. Sorry, keep trying to think here. If I do y cubed equals y from cubing both sides, then that gives me y cubed minus y equals 0. Factor a y out, gives you y squared minus 1 equals 0. And so you get y plus 1, y minus 1, 0, so I've got y equals 0, and negative 1, and positive 1. But the negative 1 doesn't make any sense because I'm not going down here at all on my graph. Okay? So my y value is going to be going from 0 right here to the 1 right here. So those will be the bounds on my integral. Sorry about the other, just looking at this in a slightly confusing manner here, trying to make it harder than I needed to, sorry. All right, so What I'm doing then is looking at going around this axis. Okay? When you're going around an axis other than the X or Y, you need to always think about going back to the X or Y axis and then coming back again. Okay? That is this right here is your outside rotation. And so we're going to want that solid minus the inside rotation right in through here. Okay? So we go all the way back to the X or Y axis, in this case the Y. That is a 1, and then you subtract off this right here. So I am revolving, it is to apply, it is integral from 0 to 1, but that outside is going to be a radius of 1 to get all the way back to the Y axis, minus that line right there is my Y squared. Okay, so there's going to give me my cone in solid form that swirls around the line x equals 1. Minus, okay, I'm going to drop down a little bit because I'm running out of room. I've got to subtract out this inside one, but again, what I need to be doing on this is going all the way to the 1 and then back to that axis. Subtract, or back to that function, subtracting off that curve. So it'll be minus 1 minus, and that curve is the cubed root of y squared, and then everything is, of course, dy, and hopefully you can see that kind of blends in there. All right, so rewriting this to make sure that you can all see it, this is pi integral from 0 to 1 of 1 minus y, that whole thing squared, minus 1 minus the cubed root of y, that whole thing squared, dy. Okay, you didn't have to solve it on this one, I just asked you to write the integral. Okay, next one, region enclosed by y equals x and y equals x cubed. It's rotated around the line x equals -3 in order to form a solid. Okay, well, I've got the same region, okay, y equals x cubed, but this time I'm going around a whole different axis, okay? Here's my basic graph, coming out with y equals x, and back with my x cubed. Oops, sorry, I didn't quite get it to go all the way down to the x-axis there. But I'm going around a line over here, okay? Now then, I made my 1 really big here, so I'm not going to be able to do that or I'll run out of room. But let's say that right here is my -3. Now what I'm rotating around is, I'm still not going to be able to do that. I've got this funny shape that looks like this, and then comes flat, and then comes like this on the outside. Okay, and then on the inside, I've got these little pieces cut out of it like that. Okay. So on the outside, it looks like a salad bowl, but on the inside, it's more trapezoid type bowl shape. On the outside, it's rounded edges, but on the inside, it's got these flat edges. Okay, so that's what I'm looking at, is going around this and having that big curve like that. Okay, that's not symmetrical there. Please ignore the drawing, but at least you got the idea. Okay, my integral, because I've already set y cubed equal to y up here, I already know that I'm going to go from 0 to 1. That's not going to be a big deal. I already know that because it's a volume of a revolution, it's pi times my radius squared times my height, which is always my dy. So I've got pi integral from 0 to 1 on this of, tell you what, I'm going to erase that, put it down here so that it's a little bit easier to read. Pi integral from 0 to 1. Now then, what we were saying, if you're going around another axis, then to find the outside axis, you go from your axis of revolution to the either x or y axis, and then, you know, on the other one we had to come back like this, but this one doesn't. This one goes on. I'm going all the way over to here to that outside axis. So this time I've got from -3 to 0 is 3. From -3 to 0 is 3 plus this curve right here. Okay, so this piece right here is going to be 3 plus that cubed root of y squared. Okay, because I'm moving to the right 3 and then going further, adding that cubed root of y. Okay, I am still taking this inside part out. Okay, so I'm subtracting this whole out of here. But when I do that, if you notice, again, I'm going from 0 all the way over, or from -3 all the way over to 0, and then plus a little bit further. So when I subtract this, it's still going to be 3, and then plus, oops, sorry, not minus, plus my function there, which is a y squared dy. Okay, and so that's how you're going to set these up whenever you're going around a different axis. We've got to be sure that we understand that. All right, moving on. Okay. These were disc reminders. Hopefully we're good on this. We're going to get going pretty quickly here. There was that. Sorry, still going. Okay, volumes by cross sections. If you're looking at this right here, this base is a circle, but my shape above it is a triangle. Okay. This base is a circle, but what I've got is a bunch of little squares added together to make this. Okay? This should look familiar. We should have looked at this in class, but I'm adding these squares together. They just end up giving me a round shape on the bottom. This one is a bunch of squares added together down here. Okay, a bunch of squares, but it's on this funny little curve shape for my function. Okay, so this is what we're looking at with volumes of cross sections. Square cross sections. I need to find the volume of the solid whose base is the region inside the circle x squared plus y squared equals 9 if the cross sections taken perpendicular to the y-axis are squares. When you draw this, draw your base. My base is a circle with a radius of 3 centered at the origin. This is my base right here. Okay? Now what I want you to do is to use your imagination and think, I have squares coming. This is the base of my square, and then it comes out from the board right towards your face. Okay? I have a square that comes out towards your face, across, and back again. Okay? So trying to, give you the impression. Okay, it looks something like that, but it's standing straight up from the board, like I laid a sheet of paper, like I put the bottom edge of a sheet of paper and came out with it. These are really hard to visualize, so I want to make sure we're good. Okay, so that's my little piece that I'm cutting. When you're looking at these, your volume on these is going to be the integral from, in this case, C to D, because I'm going to be doing it's perpendicular to the y-axis, so I have to be doing things in terms of y. And then I want the area of the shape that it gave me in terms of y. Okay? Area for any square is side squared. Okay? Because it said this was a square, that shape that came out. My area for that shape is side squared. Okay? Now then, what I'm looking at on this is that my this length right here, okay, is just trying to think how to say this. This top half right here is going to be the square root of 9 minus y squared. The bottom half would be the negative square root of 9 minus y squared, wouldn't it? Okay. Now then, the length of that side is going to be, this. Would y'all please just forgive me and let me do this again? Because I was doing it in terms of y instead of in terms of x.
it's x equals my 9 minus y squared. So there's my half right there. This over here would be the negative right here, okay? And I don't want the negative. I wanted everything in terms of x. So there's what I'm looking at. So this right here being 9 minus y squared, this base then would have to be 2. Okay, my length of my side would be 2 square root of 9 minus y squared. And we'll hit this again in class since I'm doing such a pitiful job. Please forgive me. Normally I would re-record, but I'm running out of time today. Okay, so side is square root of 9 minus y squared. That only gives me this piece, so I have to double it to get that piece right there as well. I'm going to square it, so my volume on this is going to be the integral from, in this case, that C to D is from down here to right here. So that's from negative 3 to 3 of my side to square root of 9 minus y squared. Squared, because my formula was side squared. Okay? Since one of my sides was 2 squared of 9 minus y squared, it had to be squared. And then dy. Okay? When you square this, the 2 squared would give you a 4, and you can pull that out to the front. From negative 3 to 3, and then this becomes just 9 minus y squared dy. Because when you square it, the square root's gone. And so y'all could integrate that without any trouble. Okay? Well, let's see if I can do a little bit better job on the next one. Okay. We want to find the volume of the solid whose base is the region bounded by the lines x equals 4y plus 4 and x equals 0 and y equals 0 if the cross sections taken perpendicular to the x-axis are semicircles. Again, these are really hard to visualize. Always draw your base. Do not try to draw the semicircles. They're coming out of the board towards you. Draw the base. Okay, I have a line x equals 0. That's going to be my y-axis. I have the line y equals 0. That's going to be my x-axis. And I have the line x plus 4y equals 4. Okay? And if I graph that line to find my x-intercept, remember you cover up your y, and so you would get 4. To find your y-intercept, you cover up x, and so your y is 1. And so your line comes down like that. And so I have this nice little triangle here. Let me draw that triangle in a little bit different color so you can see better. Okay, so there's my triangle right there. Now that what happens is that I am taking a semicircle right here that sticks out, okay? Half of it is going to stick out toward you, okay? So that means they're getting smaller and smaller as I go, aren't they? Smaller and smaller little semicircles, okay? Imagine that you took a piece of pizza and you cut some little half circles and you stood it up all the way down your slice of pizza, little pepperonis that keep changing shape, and you stand them up on the pizza sticking out at you. Okay, that's what we're looking at here. All right, so this one, because I'm going perpendicular to the x-axis, has to be in terms of x, so it's going to be my integral from a to b. I'm not doing any rotation on these, so I don't need the pi, I don't need the radius squared. I'm just integrating the area of one of those semicircles all along the function. Okay? Area of a semicircle, it isn't from A to B this time since I'm going perpendicular to the x-axis. Okay? Area is pi times radius squared divided by 2 because I wanted a semicircle. Okay? For this to be able to work, I'll need to solve my equation for y. I've got x plus 4y equals 4. So y is going to equal 4 minus x over 4. Now then that, remember, is my entire diameter. My equation, however, called for the radius. Okay, so I've got to cut that in half. So my radius then on this circle is going to be 4 minus x over 8. Okay. So volume is going to equal the integral from, and we've already talked about this because we said that this was 0 right here and that this was 4, so I'm going to integrate from 0 to 4. My equation this time does have a pi in it. I'm not doing pi because I'm doing the volume of revolution. I'm doing pi because it was part of my formula. So pi times my radius squared, so 4 minus x over 8 squared, all over 2, which I could pull out to the front. I probably will here in just a second, because a semicircle is half a circle. Okay? So then that's going to give me pi over 2 integral from 0 to 4. And you want to FOIL this out so that you have 16 minus 8x plus x squared all over 64. Okay, if it were me, I'd probably now pull out the 64 and just integrate it normally. So pi over 128 integral from 0 to 4 of 16 minus 8x plus x squared. Okay, and y'all can integrate from there. I do want to give you a formula that you will probably need on your homework, and it is used a lot on the AP exam. The area of an equilateral triangle. Area of a circle or a semicircle, those are easy things. Area of squares, we know those. They love to use area of an equilateral triangle because so many students do not know the formula. Okay, your formula is square root of 3 over 4 side squared. That is an equilateral triangle. Remember, all sides are the same. Okay, that's the shortcut formula without you having to stop and figure it out. Okay, all right. This is one of those pages that you want to stop and make sure you get down. If you are taking your cross-section slices perpendicular to the x-axis, okay, when you're looking at it right here, they are standing straight out at you perpendicular to that right there. Okay, then everything has to be in terms of x. You go from A to B, okay, like this, okay, and your function has to be in terms of x. Okay, A is your left region, and B is the right bound of your region. If you're taking cross-sections that are perpendicular to the y-axis, in other words, when I look like this, my cross-sections are perpendicular right there. Okay, then that's going to be integral from C to D, A of y. A of y is your representative cross-section. Function has to be in terms of y, and then your C and your D, just like when we were doing our other problems. Okay, your formulas on these are not always pi and something squared like the others because you are not revolving anything. You find the area of the cross section. Okay. All right. Homework and take-home quiz is due, but that's it. Please let me know if we have questions because this is hard stuff. All right. See y'all later. Bye.